Let's play one mind-blowing game. Firstly, randomly place 3 dots. We'll call them A, B, and C, and put a 4th dot inside of the ABC triangle. Now, let's randomly choose one A, B, or C angles and put a dot halfway from our dot to one of the angles. And continue this action to every next dot. At first blush, it seems that dots are placed in a very chaotic way. And after a long period of time, dots will fully fill the triangle. But if we speed up the process, we are starting to see an astonishing pattern. There is a huge amount of triangles that are inside of our triangle. It looks as beautiful as it is frightening at the same time. And as we enlarge and get closer to every triangle that is inside of it, there will be an infinite amount of triangles inside. And if we take other examples, by originally placing 4 dots or more instead of 3, or by playing with the initial rules and going by a 3rd or 4th of the way, we can create a more and more stunning and strikingly gorgeous pattern. And as we get close to them, they will repeat their patterns forever. And all this beauty is called fractals. And the not less interesting part is that they are not 1, 2, or 3-dimensional objects. If we take a look at our first fractal that we created, it is called the Sierpinski triangle. It is 1.58 dimensional. But how is that? If we take a 1-dimensional line and divide its size to 2 same parts, we will get 2 parts that are half size of the original line. And this information is taking a major factor in its dimension. If we take a 2-dimensional square and measure the amount of squares that are half of its length, now we will get 4 parts. And if we do the same with a 3-dimensional cube, we will get 8 parts. And then, to measure the dimension, we need to find out what degree we must put the scale factor to get the right amount of shapes that are similar to the original figure. But with the Sierpinski triangle, with the length of half of its figure, we can divide this figure only by 3 same parts as the original. It's 2d equals 3, and by using logarithms, we find that d in Sierpinski triangle equals around 1.5. Therefore, objects could be not only 1, 2, or 3-dimensional, but also in between them. Fractals are also the main instrument of nature. For instance, rivers, mountains, clouds, seashells, and leaves are also fractals. Our nature is full of fractals. For example, by taking 2 triangles that are flipped to each other and doing the same as we did with the Sierpinski triangle, with a probability of getting closer with a dot to the corners of the right triangle and small probability flipping to the left triangle. With a long period of time, we will get a fern. And nature uses fractals to create itself. That's the real beauty of fractals. But that's not the most mind-blowing information. Let's take a look at the Mandelbrot set, one of the most popular fractals. It was created in a very interesting way. If you keep squaring a number, it will quickly become a very large number. The numbers 1 and -1 act as boundaries. Beyond them, the value will continually decrease towards 0. But if we place another axis with imaginary numbers and create a 2-dimensional graph, the number on this graph that we are squaring in the boundary is sort of going around the circumference, with a boundary now looking as a circle after which the number is not stable. But if C in this formula is not a 0, then the boundary becomes such a beautiful and strange structure called Julia set. More shockingly, if the orbit of a critical point becomes 0, And if we paint the areas where states are different by stability, then we'll get such a boundary that looks like this. And this is a fractal that if you zoom in, you will get really striking pictures. There is actually even a 3 hours long video on YouTube with zooming inside of the Mandelbrot set. And in much areas, if you zoom, you will get small Mandelbrot sets. The more interesting thing is that this small formula, which is called logistic map, shows a prediction of how a population of animals will grow or shrink over time. On a graph, it creates a breakdown into different graphs, and if you zoom this graph in, you'll get a fractal. And logistic map and Mandelbrot sets are pretty much the same thing. Oh, you can't see that, but if we turn this, now you see the beauty of it. As infinitely complex objects that are self-similar across all scales, they show dynamical systems in all their honor and form part of visual representation of chaos, a behavior of certain dynamical systems that are highly sensitive to initial conditions. And a chaotic system is a deterministic system that is nearly impossible to predict. A classic example of a chaotic system, such as a chaotic pendulum. A chaos pendulum usually consists of 2 arms. The first arm is attached to a pivot point, allowing it to swing in a circular motion. The second arm is attached to the first arm's free end, allowing it to swing independently. Both arms can move freely in 2 dimensions. When the pendulum is set into motion, it exhibits complex and unpredictable behavior. Even small changes in the initial conditions as angle or velocity can lead to vastly different trajectories. Therefore, it's not possible to repeat the same pattern 2 times. Do you still think that chaos is negligible? You must be wrong. Because chaos is everywhere, from the wild weather patterns up to the unpredictable splash of morning coffee. Expanding the understanding of the fields of biology, the power of chaos cannot remain unspoken. And at the heart of this discourse, we stumble upon the concept of reductionism. The original adherents of reductionism were ancient Greek materialists, Democritus and Leucippus. Reductionism is a philosophical approach when you're trying to understand a complex system by breaking it into smaller pieces. Such plants and animals can be reduced to cells. Cells can be reduced to molecules. Molecules can be reduced to atoms. In the 20th century, most philosophers considered reductionism as the easiest way to comprehend various fields of science, even though chaos theory argues that there is no ultimate end to reductionism. At some point, systems will eventually become random, and subsequently, the Heisenberg uncertainty principle arises. The Heisenberg uncertainty principle states that the more precisely you can measure one variable like speed of an electron, the less accurately you can measure the second corresponding variable like position of the electron. This discrepancy happens not due to the flaws of our measurement tools, but due to intrinsic features of quantum systems. Delving deeper into the essence of chaos, these biological intricacies also resonate in more complex systems, as we find in the celestial bodies of our universe. In 1687, Isaac Newton published his Principles of Mathematics and Natural Philosophy, where he first mentioned the n-body problem. Let's take the Sun and the Earth as our 2 objects. This is a 2-body problem that can be solved analytically, leading to stable and predictable orbits. But inclusion of a 3rd orbit, for instance, the Moon, would lead to a problem with predicting where the system is going to be. It actually looks like this. Furthermore, astronomers claim that our galaxy is moving towards the center of nearby galaxies called the local group at 1.3 billion miles per hour. And motion towards other groups of galaxies is caused by gravity pull and a huge concentration of matter in this direction. As we travel through our galaxy, we may be surprised that this is not a straight path at all. In fact, there is an insight made by one person that changed everything we thought we knew about predictability. The American mathematician and meteorologist Edward Lorenz began simulating weather patterns using just a digital computer. His simulations consist of 12 variables, representing elements like the wind speed and temperature, aiming to observe the sequence of data again. Before Lorenz, weather prediction leaned heavily on empirical and statistical methods. Meteorologists believe that using rudimentary computer models, accurate long-term forecasts were possible. Many believed that the atmosphere's behavior, though complex, was ultimately deterministic. But Lorenz's work disrupted this confidence, introducing unpredictability into the equation. Afterwards, Lorenz invented an attractor that represents these equations. An attractor sets values toward which a system tends to advance, regardless of its initial conditions. The Lorenz attractor is the creation of a strange attractor in a three-dimensional space. Strange attractor has a fractal structure. It is non-periodic, meaning the system never settles into a repeating pattern. No one knows where the system will occur, and that's why it's called strange attractor. The strange attractor arises from a set of three ordinary differential equations that represents a simplified model of atmospheric convection. These variables symbolize the convection roles in the atmosphere, and T is time. The parameters sigma, rho, and beta are constants that determine the behavior of the system. Lorenz discovered the values of rho equals 28, sigma equals 10, and beta equals 8/3, and initial conditions of x equals 0, y equals 1, and z equals 0 to be the best representation of the Earth's atmosphere. Now you can see that the graph resembles an actual butterfly. Lorenz thought that using previous predictions to forecast the weather would simplify the system. For example, if the machine computed that the wind speed tomorrow is 3 kilometers per hour, then the system would take these results to forecast the wind speed for the day after tomorrow. The system calculates numbers up to 6 significant figures, but the machine prints and takes into account only 3 significant figures. However, when these calculations were put into practice, Lorenz was horrified with the results. Even a tiny difference, akin to the flap of a butterfly's wing, wreaked chaos in the weather forecasts, leading to a drastically wrong result, such as tornado prediction. This phenomenon was called butterfly effect, the idea that small things can have a big impact on complex systems. In the orchestra of existence, where a single note can change the entire melody, Lorenz's findings reveal a profound intersection between math, the natural world, and the mystery of existence. His breakthrough showed that life's essence lies within its unpredictability, where each moment is shaped by countless amount of unforeseen forces. Remember, chaos shouldn't be feared. From tiny actions like a wingspan, we can make the largest changes in the world, and you can start making the changes by donating to our charity fund.